Hello, my name's Jacob Child. I'm going to share about pressure prediction by a convolutional neural net. I have a lot to go through, so I'm going to blow through here pretty quick. Basically, we need pressure. It's important to better understand what's actually happening in a flow field. Flow visualization generally focuses around things that give you velocity, so predicting pressure from a velocity field is important and relevant. One of the common ways to do that is particle image velocimetry. It's when you seed particles into a flow like a wind tunnel, and then you use a laser sheet and a camera, and you take two pictures really quick after each other, and then you track where the particles move in that between the two images, and from that you get a velocity field. But there's no pressure data in there. Predicting pressure from PIV data and from velocity data generally is a great application of neural nets and convolutional neural nets and physics-informed neural nets. We have a paper on the left that exemplifies that and a paper on the right that does as well. We actually did something just like this in class. We followed this paper that used MRI vascular data. I can't remember if it's synthetic or real. And then they upscaled it and predicted an upscaled version of the U and V components of velocity, so X and Y components of velocity, as well as a pressure field. They did that by training the neural net on the Navier-Stokes equations, the 2D versions of the Navier-Stokes equations. But they note in the paper that the pressure field that they predict is actually incorrect, and then they gave some advice on how to make it better. So I wanted to predict a pressure field. To do so, I was going to use the same method that they did in the paper. Same setup, I added extra channels and an extra layer in the middle. Other than that, it's essentially the same setup as a paper, which we already know from the homework gets us good results. I also modified the learning rate depending on the test. So when I move forward with this method, I'm going to apply it on 4 different things. We're going to basically copy the paper, but I'll dig in more to the pressure results. That's part 1. Part 2 is instead of predicting U, V, and P, I'm going to give my neural net the high resolution CFD U and V data and have it predict the pressure field P. Because that's ultimately what I want to look at, what I want to learn about. Once I learn how to do that, then I'm going to apply the same principles to PIV data. I have a side view dataset and a wake view dataset from Nathan Welker in my lab. So starting with the super resolution, we're enforcing the boundary conditions in this case. So the boundary conditions are hard-coded for each of these equations. This gives us the following results. You'll remember this from the homework. We have on the top row, there's our U magnitude. This is what was predicted. This is the actual. Here's the error. You'll notice that the flow looks pretty good. This center is obviously a lot faster because we don't know boundary conditions. We hard-coded a velocity inlet and a pressure outlet. Here, this obviously isn't a fixed velocity. So we're not really sure what they're doing there. It looks like our walls are pretty good, but the error goes up, which means we might have different wall boundary conditions as well. You'll see the predicted pressure field, not much is happening. It's very far off from this, and the error is very large. That's because if we look at the Navier-Stokes equations again, they're driven by a difference in pressure. So when there's no reference pressure, the neural net or whatever doesn't know what to predict. There's a bunch of numerical methods focused around using this, the pressure-Poisson or the elliptic equation of pressure. Pressure-Poisson equation, sorry. And what these numerical methods do is they iterate through the flow field using boundary conditions that you have to estimate to try and predict the flow field from a given velocity field. So we're going to give these pressure-Poisson equations to the neural net and see what it can predict and how it will help. This is the same neural net as before. You'll notice right off that this flow field looks quite a lot better than the one before. It's got some weird lumpiness, I guess, but it looks a lot more realistic. The error goes down. Our predicted pressure also looks okay, but when you look at the color bar, we're at the wrong magnitude and our error is very large. So the neural net still doesn't have a reference pressure, and it still doesn't know what to do. So I wanted to now focus just on predicting pressure. I got rid of the boundary conditions. They're not hard-coded. And we're giving it high-resolution CFD data to start. So it's no longer upscaling. We're giving it the info that it needs, and it's just predicting pressure. On the top, just like before, the pressure field looks quite good now. It learned a lot faster, more or less, but there's still no reference pressure, so the values are quite far off. This is where the pedo probe idea comes in. What if we could give a neural net a peek at what the actual answer is? So we're going to put a pedo probe or like a pressure probe in the flow field and give it some of those values. So I said, okay, we'll do it down the middle. both ways. And that's what's on the bottom. And now it has reference pressures. It may not know the boundary conditions, but it has these pressures that it can match. And that makes the pressure field a lot more accurate. The color bars are a lot closer, and it makes our error go down. Then I wanted to know, okay, what if we let it peek at specifically the outside boundaries, where those boundary conditions might be? And that's when we get our best looking pressure field right here. It's quite close, and our error goes drastically lower. So this is good. So I took these principles and said, okay, what if we apply this now to real PIV data? We're going to predict a pressure using velocity inputs at whatever resolution we're given, and it's going to learn a pressure field by using, X and Y momentum of the Navier-Stokes equations, as well as the pressure Poisson equation from earlier. So here's what the PIV setup looks like. There's my little drawing from earlier on the left. On the right is the U velocity of this actual PIV field, and then you can see these black circles are where the PIV data is, and then you can see these cool little tip vortices shutting off. So that's kind of like where the propeller is, and this is the flow field behind it. This is the CFD data that we have to compare to. The left is U, and then the right is pressure. So here's our first result. You'll notice right off that the color scales are, well, I made the scales the same, but that the color on the left-hand plot is generally darker. We have a higher pressure everywhere over here, more or less. And then the other glaring missing part is this long streak. That's because for our PIV data, we only have X and Y components of velocity. There's no out-of-page components of velocity. So we're missing that center vortex that's shedding from the propeller that the CFD captures. We do get those tip vortices here, here, and here, which is awesome. But the magnitudes are also a little bit different. Some reasons that this may happen comes from the next slide. So black and blue are our pitot probe actual pressure data, and then red is what the model learned. So it matched the pitot probe data quite well. Even though it doesn't have boundary conditions, this becomes its boundary condition. The problem is PIV data and CFD data are basically unsteady, but pitot probe data is not. It's a time averaged thing. So that means that your average pressure isn't going to catch those unsteady effects that could be a lot lower or they could be a lot higher. And so in the end, you're going to raise the pressure of your whole field, which is kind of what we saw. I wanted to just double check, hey, is this something to do with model size? So I doubled the number of channels for each layer and ran it again. And then here's the outputs. You'll notice they look semi-comparable, but yet again, the actual, even though the general form of the flow of the pressure fields are the same, the magnitudes are off. So now we did the same thing for the wake view data. Here's what our input is. Now we're looking at a laser sheet, like into the page, top down, right after the rotor, and then we have PIV data straight through. So that's where the rotor, you can imagine, is right through the middle of, right above the pitot tube line, actually. We also, in this case, have a Z component of velocity. The PIV data is on the left, the CFD is on the right. Notice that those are actually different. So there's some differences between the CFD and the PIV data that we're giving the neural net. When we run it, these are the results that we get, and they are not super great. They're squashed, they're not square plots. I apologize for that. But on the left, things are a little funky. We should have a high pressure region here where the tips of the propeller are, followed by a low pressure region. But instead, we have a low pressure region, then we've got a high pressure region here, and it's kind of just, and here it looks okay-ish. I'm not really sure what's going on. The general shape is like, oh yeah, it's right, but all the magnitudes are wonky. It almost looks backwards. However, it is yet again matching the pitot probe data. So this may be a case of where something might not be aligned between the pitot probe data and the CFD data, or maybe there is something I misunderstood about Nathan Woker's data set. Just to double check and look at something else, I said, okay, what if we take out the W component, the Z component of velocity? What happens? And you'll see between the plots, they actually train comparably the same. But with the W, you get slightly lower losses and less oscillations. So it's important to include all of the data that you have, which is what you'd expect. So in conclusion, it's totally possible to learn a pressure field from using a neural net from velocity data, especially when you're giving it pitot probe data. That really helps. Improvements, we've got to figure out the time average versus unsteady thing. There's also some sort of data mismatch, and then I never applied Rhea-Chow interpolation. Thank you so much.